Hi, so this is the last subtopic of chapter 1, which is 1.4, elasticity. Okay, so elasticity, by definition, is the property or the ability of a material that enables the object to return to its original shape and size after the force applied to it is removed. So here are some examples of objects that have elasticity. So these objects, when we exert force to it, when we squeeze, we grab, push, pull, or any action taken to it that causes the shape and size to change. So when we remove the force, these objects will return to its original shape and size. Okay, so now we're going to take a look at an experiment to investigate the relationship between force and extension of spring. So this is the experimental setup. So here you can see we have a spring, a pin, a plasticine, half-meter ruler, table, and retort stand. So without the load, okay, so here the load is plasticine. So without the load, we will get the original length of the spring, which we label as L naught. And then when we place the load, which is a plasticine of a certain specific mass, the spring will extend to a certain length, which we can call as L1. So the experiment here is to investigate the relationship between force and extension. And an extension here is given by the length of the load is placed minus the original length. Okay, so this experiment actually can be used to describe Hooke's law, where Hooke's law states that extension of a spring is directly proportional to the force applied on the spring, provided that the elastic limit is not exceeded. Okay, for example, let's say we've done the experiment and this is the data that we obtained. 2 Newton, extension 0.05, 4 Newton, extension 0.1, and so on. So from the data here, we can observe that for every 2 Newton, extension will increase by 0.05 meter. Next, when you plot a graph based on the data, so it is true that Hooke's law states that the relationship is directly proportional. So for every Newton, spring extends by 0.05 meter. Okay, so back to Hooke's law. So from this graph, if we want to find the gradient equation, which is y equals to mx plus c, and y here in this graph is represented by f. M, we don't know what m yet, but it's going to be the gradient of the graph. X is represented by x, which is the extension of the spring, and then c, which is the y-intercept, 0 here. So f equals to mx. So if you want to find the gradient is actually f over x. But in Hooke's law uses k instead of m, equals to f over x, where k is the constant. The gradient is a constant value, which we call as spring constant. And it has unit of Newton per meter based on the formula here. Okay. The other information that we can obtain from the graph here is the elastic potential energy of the spring. So here, to find the elastic potential energy of the spring, we only need to find the area under the graph. So here, area under the graph that I am highlighting using blue highlighter. So this area under the graph is the elastic potential energy, which we need to find using the formula, a simple formula, because this is what we can see is here is a triangle. So the formula of the triangle here is 1/2 times f here times x. So that is your area under the graph. Okay, let's transfer to the formula. Okay, so elastic potential energy is half times F times X. Another elastic potential energy formula that we can use is, okay, so from Hooke's law formula, F equals to Kx, we can substitute this formula in the first formula here. Okay, so we substitute F equals to Kx in 1, so you will get half Kx times x, which is half Kx squared. So now you have two formula to express elastic potential energy. Okay, so now we are going to do a few problems involving Hooke's law. Question number 1, you are given a graph of force against extension. So the question asks, calculate the work done to stretch the spring of length of 0.03 meter. So the work done here is actually equivalent to the elastic potential energy. So to find the elastic potential energy, you need to find the area under the graph. So area under the graph is represented by half times f times x. Half times 2 times 0.03, you will get 0.03 joule, because the unit for work done or unit for energy is joule. So the next question, find the constant spring of the spring, which can be found by calculating the gradient of the graph. Okay, so to calculate the constant spring, we can simply use formula F equals to Kx, or you can use the formula EP equals to half Kx squared. So either one, since you already found the elastic potential energy in the previous question, which is 0.03, we can just substitute that in the formula. EP is 0.03 equals to 1/2 times K times X. So X here, you can use the maximum value 0.03, because in the previous question you used 0.03. So X times 0.03 square. So K here, you will get 66.67. So the unit is Newton per meter. Okay, next, second question. So here, in this question, instead of extension, the question shows us that the spring is being compressed, which is also applicable if you want to use Hooke's law. So calculate the force constant of the spring. So first you have to find the extension, but in this case the spring is being compressed, so you have to find the compression. So compression is 10 minus 6, which is 4 centimeter, and don't forget to convert to SI unit, which is 0.04 meter. Next, you also need to find the force. So given that gravitational acceleration is 9.81, so force is mass times gravitational acceleration. So 1.5 times 9.81, which is 14.715 Newton. Okay, so to find the constant spring, we can simply use Hooke's law, F equals to kx, k equals to F over x. So k here is 14.715 over 0.04, and you will get 367.88 Newton per meter. Okay, next question. What is the elastic potential energy stored in the compressed spring? To find the elastic potential energy, you can use formula EP equals to half Fx, or you can use EP equals to half Kx squared. Since you already found the value of K from the previous question, I think I'm going to use the second formula. EP equals to half times 367.88 times x. So x is given 0.04 square. So you'll get 0.294 joule. Okay, so that's all for this video. We're going to continue with the second video.